The rock of the asthenosphere beneath the site of a splitting ridge, in fact beneath any piece of lithosphere, is this kind of rock that we have here. It's a rather green-looking rock with some brown crystals in it. They're in fact crystals of garnet. The green background is formed of the minerals olivine and pyroxene, and that's the rock that we think makes up the asthenosphere. Let's put those minerals, the garnet, the pyroxene, and the olivine, beneath the diagram there, and see what happens when that rock melts. Garnet, then, is one of the main constituents of the rock of the asthenosphere. The others are, we think, pyroxene and olivine. Now, when that rock of the asthenosphere melts, the process is just as complicated as I described to you a couple of minutes ago. Briefly and simply, what we think happens is that calcium and sodium are released from the pyroxene, and they go to form that part of the liquid which will eventually crystallize as plagioclase. And the sodium and calcium from the pyroxene are accompanied in the liquid by aluminum, which is derived from the beginnings of the melting of the garnet. So that these two minerals, these two, the pyroxene and the garnet, as they begin to melt, contribute to that part of the molten material which will eventually crystallize as plagioclase. The pyroxene, having lost some of its sodium and calcium, when it eventually melts and then crystallizes again, forms a different pyroxene. The olivine, although it doesn't actually behave in detail like this, you can regard as having simply melted and recrystallized again. And these minerals, plagioclase, pyroxene, and olivine, derived from the beginnings of the melting of the asthenosphere, form the rock basalt. And that then is what we think, approximately simplified, happens at a spreading center like this. The asthenosphere begins to melt. About 10% of it probably melts and forms the oceanic lithosphere.